This is AP Calculus 2.4, and we're talking about differentiability and continuity. Now, remember, in continuity, that's when a function is continuous. So there were several things that destroyed continuity, or that said that the function was not continuous. Asymptotes, holes, or jumps in the graph. And we talked about those in the first unit. In this unit, we're going to determine when derivatives do and do not exist. And there are several things, there are actually 4 things that destroy differentiability. And the main thing you need to know is if a function is continuous at the x value where you're trying to find the derivative or you're trying to find the slope of the tangent line, it's only differentiable at that point if it's continuous at that point. If it's not continuous at your x value for the function, it won't be differentiable at that point either, okay? Now, that doesn't mean that just because there's an asymptote in the function somewhere that it's never differentiable. That's not true. What differentiability relies on is that it is continuous at that specific point on the function, not that the whole function is continuous, okay? So that's something totally different. So if we're looking to see if a function is differentiable at a specific point, it's most of the time differentiable at that point if it's continuous. Now, there is a special case to that, and I'm going to talk to you about that today. But the 3 real simple ones that I'm going to talk to you about first are things that destroy differentiability at a point, and they are vertical asymptotes, a hole or a jump in the graph, and a vertical tangent line. Now, these 2 we've talked about extensively already. We've talked about how to find horizontal and vertical asymptotes, and we talked about how to find holes or jumps in the graph. Usually the jumps occur if it's a piecewise function, sometimes occasionally in absolute value type functions. It depends on what they give you though for those. A vertical tangent line though is a function that when it's graphed looks like this. And you can see there at this point right here, there's going to be a vertical tangent line in there that destroys differentiability, okay? And it doesn't happen very often, but if in this case x was equal to 0 there, I didn't draw it perfect, but if x was equal to 0 there, you would have a vertical tangent line, and which means your tangent line would be found to be undefined at that point. In that case, it's not differentiable at that point, okay? And then the 4th one is what happens when there is a sharp turn in the graph. With a sharp turn, that's a little bit different, and so I want to make sure I spend a little bit more time on sharp turns because there are some things there that you need to consider before you go any further. So the 4th thing that destroys differentiability at a point is a sharp turn in the graph. And the most common example of that is an absolute value graph. If you think about that, in an absolute value graph, let's just say that I graph it and there's my absolute value at graph. And this point right here, let's just say that's A. So this would be A, the point A, f of A, and it's an absolute value function. Well, if I'm trying to find the derivative of that point, or the slope of the tangent line at that point, if you think about that, isn't there an infinite number of slopes that I could attach to that tangent line? Because there's not just one tangent line on that sharp curve. So a sharp curve here destroys differentiability. Now, it's differentiable everywhere except for that point, because the slope of that side would be a specific slope for the entire side of that line. The slope for this side of the line would be a specific slope for that entire part of the line. But at that specific x value, there is not a function that is differentiable because that sharp turn keeps us from having one specific slope at that point. So that's the easiest way, kind of the simplest explanation I can give you. Another place that you might have a sharp curve or a sharp turn is often in a piecewise function. Let's say in a piecewise function, maybe the first part of it does this, and then the second part of it is just a straight line. Maybe it does something like that. Well, again, right here we have a sharp curve. That's not differentiable at that x value. Because of the sharp curve, there's no way to tell what one specific slope that derivative is going to have at that point. So you can't have differentiability if you have a sharp curve. So differentiability implies that the function is continuous. In other words, it has to be continuous in order to be differentiable. But just because it's continuous does not mean that it is automatically differentiable. In an absolute value function, it'll look like that. A cusp, if you have a graph that looks like that. A vertical tangent line, and I drew that one earlier. If you have something that looks like that. And then a piecewise as well. So there are 4 different types of graphs, and there may be more out there, but there are several different types of graphs that destroy differentiability, not because they're not continuous, but because they have a sharp turn in the graph. So the things that destroy differentiability at a point: vertical tangent lines, holes or jumps in the graph, vertical asymptotes, and then a sharp curve in the graph. So those are the things that destroy differentiability at a specific point. So some examples they might give you: they may give you an absolute value function and they ask you to find what the slope of the tangent line is at that specific point where it does the sharp curve. You would have to say it's not differentiable at that point. They may give you a piecewise function and they might ask you to determine what the differentiability or what the derivative is at a specific point on that piecewise function. But the point where the piecewise functions meet is where you're talking about having a sharp curve. It wouldn't be differentiable at that point. And if they gave you any x value anywhere else on that piecewise function, it might work. But at the point where the 2 different piecewise functions come together, you're going to have a sharp curve. So it would not be differentiable at that specific point. If they give you a curve like this, and when you go to plug into the derivative, you get an undefined slope at the tangent line, then again, it's not differentiable at that point because the slope of the tangent line at that point was undefined. So there are several different cases that might be, and they'll just ask you if it's differentiable at that point or not, and you just have to determine if it's one of the special cases. If it's not, like it doesn't have an asymptote there, it doesn't have a jump or a hole, or doesn't have a sharp curve, then it would be differentiable. If it does have one of those special cases, then you have to just say this function is not differentiable at that x value. It's pretty simple, but you have to understand when a function is differentiable and when it is not.